Have you ever wondered how the massive amount of electricity generated at a power plant, sometimes hundreds of miles away, ends up safely charging the delicate battery in your smartphone? If we plugged your phone directly into the transmission lines, it wouldn't just charge, it would explode. The bridge between that high-voltage danger and the low-voltage safety of your home is a device that has no moving parts, makes no noise other than a quiet hum, and is arguably the most efficient machine ever invented. I'm talking about the transformer. The principle of transformer operation. Today, we aren't just skimming the surface. We are going to break down exactly how a transformer works, from the atomic behavior of the magnetic core to the mathematical equations that govern its voltage. By the end of this video, you will understand electromagnetic induction, mutual flux, and exactly why we need different types of transformers. Let's dive in. To understand a transformer, we first have to go back to 1831 and visit Michael Faraday. The entire operation of a transformer relies on one golden rule of physics, electromagnetism. When an electric current flows through a wire, it creates a magnetic field around it. Now, if you take that wire and coil it up into a solenoid, those magnetic fields combine to form a much stronger, concentrated magnetic field inside the coil. This is an electromagnet. But here is the magic. Faraday discovered that this relationship works both ways. If you have a changing magnetic field passing through a coil of wire, it pushes electrons. It induces a voltage. This is Faraday's law of electromagnetic induction. Note the key word there, changing. A stationary magnetic field does nothing. You need the magnetic field to grow and shrink or move back and forth to create electricity. This is why transformers only work on alternating current, AC, not direct current, DC. With DC, the current is constant, so the magnetic field is constant. No change means no induced voltage. But with AC, the current is constantly reversing direction, 50 or 60 times a second. This means the magnetic field is constantly expanding and collapsing. This dynamic magnetic field is the heartbeat of the transformer. So, how do we package this physics into a machine? A basic transformer has two main parts, the magnetic core and the windings, or coils. Let's look at the windings first. We have two separate coils of wire. The coil connected to our input voltage source is called the primary winding. The coil connected to our load is the secondary winding. Crucially, these two coils do not touch electrically. There is no wire connecting the input to the output. The energy is transferred entirely through magnetism. To help that magnetism travel from the primary to the secondary, we place both coils on a core, usually made of soft iron or silicon steel. Why? Because iron is thousands of times better at conducting magnetic flux than air is. It acts like a highway for magnetism, guiding the field from the first coil directly into the second coil. You'll notice the core isn't a solid block of steel. It's made of thin, stacked layers called laminations. Hold that thought. We will explain why we do that in the losses section later. Now, let's flip the switch. We apply an alternating voltage to the primary winding. This causes an alternating current to flow in the primary coil. This current creates an alternating magnetic flux in the core. Because the core is a magnetic highway, this flux flows around the loop and cuts through the secondary winding. According to Faraday's law, because this magnetic flux is alternating, it induces a voltage in the secondary winding. This is called mutual induction. The amount of voltage induced depends on two things: the rate of change of the flux, frequency, and the number of turns in the coil. Mathematically, the induced EMF, E, is 4.44 times frequency times the number of turns times the maximum magnetic flux, where F is the frequency in hertz, N is the number of turns, and phi max is the maximum magnetic flux. This equation tells us something powerful. We can control the output voltage simply by changing the number of turns in the coils. This brings us to the concept of the transformation ratio. Since the voltage per turn is the same for both windings, the ratio of voltages is equal to the ratio of turns. If the secondary winding has more turns than the primary, the output voltage will be higher than the input. This is a step-up transformer. We use these at power stations. Conversely, if the secondary has fewer turns, the voltage goes down. This is a step-down transformer. This is what's inside your phone charger. But wait, if we step up the voltage, are we creating free energy? No, the law of conservation of energy still applies. Power input must equal power output in an ideal world. This means V1 times I1 equals V2 times I2. This means if the voltage goes up, the current must come down. A step-up transformer increases voltage but decreases current. In our equations, we assumed the transformer was ideal, meaning 100% efficient. In the real world, transformers get hot. That heat represents wasted energy. Let's look at the four main enemies of transformer efficiency. 1. Copper loss. $I2 or dollar loss. The windings are made of copper, which has some electrical resistance. As current flows, some energy is lost as heat. We minimize this by using thick wires for high current windings. 2. Eddy current loss. Remember the iron core? Since it's conductive, the changing magnetic field induces small swirling currents inside the iron itself. These are called eddy currents. They generate useless heat. This is why we laminate the core. By slicing the core into thin sheets and insulating them from each other, we break the path for these currents, significantly reducing the loss. 3. Hysteresis loss. As the AC current flips direction, the magnetic domains in the core have to physically flip orientation north to south, over and over again. This friction at the atomic level causes heat. 4. Flux leakage. Not all the magnetic flux produced by the primary makes it to the secondary. Some leaks into the air. Good core design minimizes this. Despite these losses, transformers are incredibly efficient. Large power transformers can reach efficiencies of up to 99%. They are the silent workhorses of the modern world. To summarize, alternating current creates a changing magnetic flux. The core guides this flux to the secondary. Faraday's law induces voltage. The ratio of turns determines the output. I hope this deep dive illuminated the principle of transformer operation for you. If you found this breakdown helpful, be sure to hit that like button. Subscribe for more engineering explanations. Thanks for watching, and I'll see you in the next one.